By 2026, your superbike is no longer just a mechanical machine, it is a software-defined vehicle. By 2026, your bike knows the road better than you do. Think of the ECU as the flight computer of your motorcycle. Just as a modern jet cannot fly without fly-by-wire technology, a 2026 superbike is unrideable without its onboard digital brain. The modern superbike functions through a central digital nervous system, the ECU. It acts as the brain of the machine. Sensors constantly stream vital data, including wheel speed, lean angle, and throttle position, into this core unit. The ECU processes these inputs in just a few microseconds. This lightning-fast reaction ensures that stability adjustments feel completely invisible to the rider. By managing the bike's mechanics at digital speeds, the ECU allows riders to push limits with total confidence. Modern superbikes function as software-defined machines, relying on a constant stream of telemetry from specialized sensors. Critical inputs include wheel speed sensors, the inertial measurement unit, and air temperature monitors. These sensors send data to the ECU in microsecond intervals, allowing for near instantaneous adjustments to engine power and stability systems. This sub-millisecond response is what makes modern electronic rider aids feel completely invisible. Modern superbikes use software to redefine performance. By adjusting the digital brain, we change how the bike behaves without ever touching a mechanical part. Rain mode prioritizes safety by smoothing out throttle response and maximizing traction control intervention. It is designed for low-grip surfaces. Street mode provides a balanced profile, offering predictable power delivery suitable for daily riding conditions. Sport mode sharpens the throttle response and optimizes power delivery for aggressive riding on winding roads. Finally, track mode minimizes electronic intervention, allowing experienced riders to push the machine to its absolute physical limits. These modes transform the motorcycle's character instantly, ensuring the machine adapts perfectly to the environment. The traction control system monitors the rotational speed of both wheels simultaneously. Under normal conditions, they rotate at identical speeds. When the rear tire loses traction, it accelerates faster than the front wheel. This speed discrepancy is immediately detected by the ECU. Within microseconds, the ECU cuts ignition power, effectively reducing torque to prevent the rear wheel from spinning out of control. Once grip is restored, the power is smoothly reinstated. This rapid oscillation occurs hundreds of times per second, keeping the motorcycle stable. Superbikes use the inertial measurement unit, or IMU, to monitor pitch in real time. When the front wheel rises, the IMU detects an increase in pitch angle, signaling the engine to intervene. The system rapidly limits engine output, cutting power to safely bring the front wheel back down while maintaining steering control. This constant balance protects the rider while ensuring the bike remains controllable during high-performance acceleration. Cornering ABS has revolutionized modern superbikes. By using data from a 6-axis IMU, the system calculates the bike's lean angle thousands of times per second. This allows for trail braking, where riders can safely apply brake pressure while deep into a corner. The system continuously adjusts braking force. As the lean angle increases, the ABS intelligently reduces pressure to prevent the front wheel from tucking. This digital safety net ensures maximum grip, allowing riders to maintain control even when braking aggressively mid-turn. Modern superbikes push engines beyond 220 horsepower, creating immense thermal energy that must be managed to maintain peak performance. The 2026 breakthrough is the transition to nanofluid coolants. These advanced liquids contain suspended particles that significantly increase thermal conductivity. Higher thermal conductivity allows for much smaller and lighter radiators. By shedding weight, we minimize the bike's mass without compromising cooling capability. This thermal efficiency is essential for the next generation of high-performance motorcycles. The liquid cooling system is a closed-loop cycle. A high-efficiency pump circulates nanofluid coolant through the engine jacket to absorb combustion heat. Heated coolant then travels to the radiator, where the high surface area allows for rapid heat dissipation into the surrounding air. In slow traffic, An electric fan automatically activates to pull air through the fins, ensuring the engine stays within optimal operating temperatures to prevent damage. The exhaust system acts as the primary exit path for combustion gases. High-speed gas expulsion is essential for clearing the cylinder effectively, which allows for optimal power delivery in every engine cycle. Modern superbikes utilize lightweight materials like titanium and carbon fiber. These reduce critical unsprung weight and manage extreme thermal loads, ensuring the engine can operate at peak performance without added mass. By optimizing the flow path and minimizing mass, the exhaust system remains a critical component in the pursuit of maximum superbike horsepower. A superbike's signature growl begins at the engine. The firing order determines the rhythm of exhaust pulses entering the header pipes. Exhaust length is precisely tuned. Reflected pressure waves return to the cylinder, creating a scavenging effect that pulls more air-fuel mixture into the engine. By matching these wave frequencies to specific engine speeds, engineers optimize torque at high RPMs, which manifests as the iconic high-pitched superbike sound. Superbike winglets are not just for aesthetics. They are sophisticated aerodynamic components designed to generate downforce at high speed. As air passes over these surfaces, they create a downward force that effectively presses the front tire firmly into the track surface. This additional grip is critical. It improves stability during hard acceleration by keeping the front wheel planted, reducing the tendency to wheelie, and allowing the rider to deploy more power. By 2026, superbikes have adopted active aerodynamics. Unlike static wings, these systems use flaps that adjust their angle in real time. On long straights, the flaps remain flat to minimize air resistance, allowing the bike to reach peak velocity. As the rider approaches a corner or brakes hard, the flaps deploy, increasing downforce to keep the tire contact patch firmly planted on the asphalt. This constant adjustment ensures the rider experiences the perfect balance of agility in corners and pure speed on the straights. Motorcycle fairings are engineered to slice through the air with minimal resistance. By smoothing the airflow over the engine and frame, they significantly reduce drag. A critical function of the fairing is creating the rider envelope. This bodywork directs turbulent air away from the rider, creating a pocket of stable, low-pressure air. By shielding the rider from direct wind blast, fairings reduce physical fatigue during high-speed riding, allowing for better focus and control on the track. Modern superbikes have replaced traditional analog gauges with high-definition TFT displays. These screens act as the central hub for the entire vehicle. They provide real-time telemetry, including engine RPM, speed, and critical diagnostics, all presented in a sleek, customizable interface. Integrated 5G and Bluetooth connectivity allow for seamless navigation, hazard alerts, and remote bike diagnostics, turning the cockpit into a sophisticated command center. Modern superbikes are no longer isolated machines. They use V2X communication to see beyond the rider's field of vision. By networking with infrastructure and nearby vehicles, the bike receives real-time telemetry, warning of hazards hidden by blind corners. This constant digital awareness creates an invisible safety horizon, keeping the rider informed of potential dangers miles before they are visible. In the world of superbikes, the industry gold standard is a 1-to-1 power-to-weight ratio. This means for every 1 kilogram of mass, the engine produces 1 horsepower. This extreme performance pushes the boundaries of human reaction time. The raw acceleration a 1-to-1 machine can generate exceeds what a rider can physically manage without assistance. To bridge this gap, modern bikes use AI-driven electronic safety nets. These systems process sensor data in microseconds, ensuring that the power delivery never exceeds the rider's capability to maintain control. Electronic suspension has transformed motorcycle handling by replacing static damping with active magnetic ride control. Inside the dampers, magnetic fluid changes viscosity instantly when subjected to a magnetic field, controlled by the bike's digital brain. This allows the system to adjust damping stiffness 1,000 times per second, effectively reading the road surface in real time. By compensating for imperfections instantly, the rider gains unmatched stability and confidence, regardless of the terrain. Modern superbikes are shedding weight through advanced material science. Moving beyond standard carbon fiber weaves, manufacturers now use forged carbon and graphene reinforced resins. By applying graphene reinforced materials to frames and swing arms, engineers increase structural rigidity. This allows for thinner components that drastically reduce unsprung weight, improving suspension response and handling. Superbike manufacturers are evolving performance through e-fuels and mild hybrid systems. These technologies maintain high output capability while reducing the environmental footprint. Internal combustion engines often suffer from a torque gap at low RPMs. This is the struggle to deliver instant power before the engine reaches its power band. Manufacturers are integrating small electric motors to fill this gap. By providing instant electric torque, they ensure power delivery remains linear and aggressive from the start. This integration represents the future of superbikes, where sustainable engineering meets pure, high-performance adrenaline. Modern superbikes are more powerful than ever, yet they have become significantly safer. Industry data reveals that the integration of advanced traction control and cornering ABS has led to a 30 to 40% reduction in single-vehicle motorcycle accidents. By intervening microseconds before a loss of traction occurs, these digital systems act as a safety net, allowing riders to harness massive performance with significantly higher confidence and reduced risk. We are reaching the electronic ceiling, where raw power exceeds human response. The next evolution is predictive assistance, where motorcycles adapt their safety interventions to the specific rider's skill level. Advanced sensors and AI will constantly analyze inputs, mapping the rider's tendencies, reaction times, and control smoothness. The safety net is no longer static. As the AI identifies higher skill, the electronic ceiling lifts, granting more freedom. For less experienced riders, it tightens to provide an intuitive safety margin. This creates a seamless loop between rider intent and machine response. The bike becomes less of a tool and more of a partner, ensuring that peak performance is achieved with maximum security. The modern superbike represents a perfect synergy. It combines raw mechanical power, a sophisticated digital nervous system, and advanced aerodynamic engineering. Which component surprised you the most? Share your thoughts below, and make sure to subscribe for more engineering deep dives into the machines that push the limits of performance.